Welcome, everybody. You are very brave, I think, for arriving at this late hour in our conference to talk about science and physics. I thank you all for coming. My name is Chris Swanson. I am a president and tutor of a place called Gutenberg College, which is a very small, classical, great books, 4-year Christian institution in Eugene, Oregon. We've been around since 1994. And one of the things that is key and central to what it is that we do at Gutenberg College is ask questions. In fact, I would say that I do quite a bit of teaching as well as administration, and in 90% of my classes, I am doing a great effort to simply ask questions and not provide information in some sense. It is different in a college environment, I think, than it is in K through 12, but that is kind of where we're coming from. My background is in physics, so that's why it's an inquiry approach to physics, but I think the kinds of things that I'm here to say would apply broadly to the sciences as well. And even potentially to mathematics. I will confess straight out that I've spent my whole entire career in higher education, so I have not taught a K through 12 science class. So I am not an expert, okay? So you guys who have been doing the teaching in K through 12 and science and that kind of stuff have more experience at that than I do. So all I want to do is offer some thoughts that I've had in terms of how I think about science and how I think about education. I've thought about those things intensely for a long time. One of the things we spend a huge amount of our time on at Gutenberg College is philosophy of science and how you know and on what basis can you claim that something is true. And I've looked a lot at the history as well. So that's what I'm going to do is I'm just going to provide you a few thoughts that I've had, and then maybe towards the end I would really like your input or maybe collaboration and thinking about some of these things. Whether these ideas are useful to you or not, I have no idea, but we will see how it goes. Okay, so, and this is also a little bit based on my experience when I was going through school. I went through high school. I took physics. I went through undergrad. I took math and science and physics classes. I went through graduate school, took a lot of physics classes, and in all of the cases, in all the classes that I took, and as I look out, I see a lot of answers and not many questions. In other words, the way science, it seems to me, is usually taught is here are the answers. Here are the concepts. These are the things that you should know. So that seems to me is the beginning of the comments that I want to talk about. There were various points in my life and history where something really engaged me. There was in 7th grade, there was a teacher that put up the year. I don't even remember what year it was then. It's so long ago. I can't do the math, even though I'm done on math. Anyway, he puts the year up and he says, here's 4 digits. I want you to take those 4 digits and you have to use every single digit exactly once. And you can use all the operations that you want, but I want you to create the number 1. And then I want you to create the number 2. And I want you to create the number 3. It was like a game. And my friends and I thought, that is the coolest game. And we had the biggest competition to see who could get the farthest. And we all got stuck at 17 or something like that. I don't remember exactly how it went, but that was fun. That engaged me. And then I remember in undergraduate, I was trying to decide, well, do I want to do physics? Do I want to do math? And there was a talk that somebody gave me. And it was very intriguing because he introduced that there were these unknowns, these questions, these things that had not been discovered about particle physics. And that engaged me. It was like, oh, there's questions. Those are interesting questions. I would like to think about those sorts of things. But when I was taking the classes, there were never questions. I mean, the only questions were how to solve this particular problem at the back of the chapter, right? There were lots of answers, And it was also a kind of a frustrating experience for me when I was homeschooling my children. I homeschooled them all the way through, and I was the one in charge of teaching math and science, and I just didn't have the wherewithal to think about what was going on at that time, and there were lots of answers, and the kids were, they were somewhat cooperative, but they weren't really intrigued. There were no questions, there were no live questions for them. So this is a real question for me if I'm thinking about high school, if I'm thinking about middle school or something. How can we teach science better? Is there a way that we can make them to have real questions? It seems like there are some problems that students face when you do sort of here's the canon of physics, here's the canon of science, and we sort of explain it on the board. I don't know what you guys do. Maybe you don't do that. I know that when I was a student, that's what it was the teacher got up and explained everything on the board. And a lot of students don't respond to that very well. It's like, I can't do that. That's too hard for me. I'm not mathematically inclined, or it doesn't work for me. It doesn't seem to be relevant to me, possibly. Maybe I don't want to use it in my later life. That's not my career path, or it's just facts. It doesn't inspire me. So I don't know whether you guys experienced this, but that was what I remember. So you'll have to tell me. I don't know. Do you guys experience any of this kind of stuff? Am I like talking to? No, does that sort of make sense? Sort of makes sense. So I think part of the problem, maybe, or one way to think about it, is that science is settled. All the stuff that we present is always settled science. It's sort of a legacy of the Enlightenment. So what do I mean by that, a legacy of the Enlightenment? One of the legacies of the Enlightenment is the scientific method. We teach that there is a method to science. And if the scientists, in some very impersonal way, follow that method, you have your observation and your question, your hypothesis, you do your experiment and analysis, and get your conclusion. You guys have all seen that kind of an idea, scientific method, and we teach that to our children, and it's part of the way that they grow up and think about it. It's a very objective, impersonal approach to science. There is no personal involvement on the part of the scientist. There's no inspiration. There's no investment in it. It's sort of a mathematical, mechanical method. And if we follow this prescribed method, then we are going to get answers. And presumably, as far as the students are concerned, all the stuff that is in the textbook has been determined by scientists using the scientific method in this very impersonal, objective way. And so the only conclusion that can be drawn is that everything that I'm being presented with is the canon of knowledge, of physics, of science, and so on and so forth. And it's just up to me to absorb it. That's what science is. Absorb the facts, absorb the concepts, absorb the techniques, learn how to solve the problems. It's all coming from textbooks. There is a lot of authority and a lot of certainty associated with what it is that what we're teaching here. Now, don't get me wrong. I am not saying that the stuff in the textbooks is all wrong. I'm not trying to say that at all. What I'm talking about here is the mood. I'm talking about the way that we think about it. I'm talking about how we think about the information that is being passed on here. That's what I'm talking about. And I'm going to give you some ways of thinking about it that it seems to me that can provide us to have real questions. I'm convinced that physics, or science in general, is a human endeavor. There is a great deal of passion involved. The scientists are not impersonal, objective machines who are simply going through rote processes in order to come to answers that they don't care about. That's not it at all. That's not it at all. They are passionate people who are committed deeply to the things that they are discovering and figuring out, and they are in a constant debate and battle with others, trying, because they are passionate and desire to know how the world works. So, a lot of this I'm taking from my My favorite philosopher of science, Michael Polanyi, who wrote a book called Personal Knowledge, somebody referred to him as an epistemological therapist for a secular age, which I think is a wonderful description of this man. What he claims is that the disinterested science is a myth. His whole title, the title of his book is Personal Knowledge. The knowledge that we have in science is personal, it is deeply personal. And that scientists cannot remove themselves from the process. They bring to the process a whole host of assumptions, all the things that they have learned, all the paradigm that they have absorbed, the skills that they have developed in themselves, the techniques that have been taught to them, the problem-solving skills that they have honed over years and years. Many of these sorts of things are inarticulate knowledge. They are things that are embedded in the mind and the heart and the body and the hands of the scientists, that you cannot try and do science without all of that stuff as a background. You can't take the human out of the scientific activity. And that part of the passionate engagement in science is that they are seeking meaning and order. They're not seeking dry facts. They're seeking ways to make connections. They're seeking ways to say, why is this the way it is? How is it that this thing has given rise to this thing? Why is it that the planets rotate around the sun in this particular way? All of these sorts of questions are questions where they are seeking and they expect, this is one of the assumptions, they expect that they will find order, that they will find meaning, that they will find beauty possibly, or be able to fit in this particular event or this phenomena that they have measured. They'll put it into a context of some sort. Because if it's just a piece of information that has no context, if it doesn't mean anything, if it doesn't fit into a larger picture, then it's nothing. It makes no sense. It's a totally meaningless tidbit of information, right? And scientists don't like that. They want it to fit. They want it to make order. The context that we're talking about here is usually scientific, but it could very well be cultural, and it often is. One of the things that we do at Gutenberg College is we go through a variety of scientific theories or scientific revolutions. I study the Copernican revolution. I also do a class on the theory of relativity and just very briefly on quantum mechanics. And in all of those cases that I teach, it is very much the case that the underlying philosophical assumptions and foundations of the people who are doing the work are determinative, not just influential, but determinative of the kind of answers that they get and the kind of solutions that they're seeking. It's hard to imagine that that's the case, but it is really true. If you look at it, if you watch what they're doing, if you read the words of the original authors, you read Copernicus, you read Einstein, you read Heisenberg, it is clear that they have certain assumptions as to the way science should be and the way that the world should work. And they are only looking for solutions that fit those presuppositions. They are bringing a lot of themselves to the practice. They are bringing themselves into the game. And you cannot remove that person out of it. They bring skill. They develop those skills. They become connoisseurs for finding order and beauty and finding connections and meaning and those sorts of things like that, and for doing experiments and for understanding data and those sorts of things like that. They become to where it's like they're like wine tasters. When they taste a good wine, they know it's good. How do they know? You can't say how you know why the wine is good, but you know it's good when you taste it. It's the same with the scientists, the creative scientists. They know when something is on the right track. They have an inkling, they have an inclination that, this is going in the right direction. Sometimes it isn't the right direction, but that's what they think. All of the major theories in physics are born in debate. We think that it's sort of this mechanical process of progress, that each particular theory is obviously true, and if you read even a little bit of history, maybe you have like sidebars in your textbooks that talk about the history of science, right? Like this physicist, you know, a little sidebar on Newton and maybe a sidebar on Archimedes, or I don't know what it is, but they always talk about the heroes. They talk about the people whose theories we still hold. When do you see a sidebar about the people that we don't agree with anymore? You don't see that sidebar. Why? Because they were the losers. But there was a debate. At the time, it was a huge debate, and it was a big question. And people were passionately involved in that debate. The helio versus the geocentric astronomy. That was a huge debate. It lasted for hundreds of years, thousands of years. Heat as a fluid versus a vibration. That was a major, major debate in the early, I think it was in the 1700s. Vacuum does exist or does not exist. Is there a vacuum or not? This was the debate between the Aristotelians and people like Pascal. And it was a big debate. Light is made of particle or waves. This was something that Newton was asking. You know, how is color made? Is it different kinds of particles, different colors, or is it different frequencies of waves? And this was a huge debate. Randomness or determination in quantum mechanics. I mean, we ended up with randomness, but at the time of the origins of quantum mechanics, it was a huge debate between Einstein and Bohr. There's a picture of Einstein and Bohr sitting there having this conversation. I think they ended up wrong on that answer, actually. I think randomness is not the right answer. So I would say that all of the major theories, and this is just a small sampling. I mean, it doesn't matter which thing you pick in your physics curriculum or your science curriculum. There was a debate, almost certainly. And there were various sides, and one side kind of won out over the other one. So that's my thinking about the nature of science and how it developed and the history and the philosophy of it. But what is the implications for that? Well, one of the implications, it seems to me, or we have to decide for ourselves actually, what is it that we're doing? Why are we here? Are we interested in giving them the facts, the things which have been passed down to us, the stuff that is in the textbooks? Is that really what we want them to learn? Because unless they carry on in that particular field for a long time and sort of it becomes a part of them, they're going to forget it. I forgot a lot of stuff. I took chemistry in high school. I took chemistry in college. I don't remember hardly any of that stuff. I had to teach it to my kids. I had to learn it all over again. What I recommend is developing the student. What do I mean by that? I feel like it could be more than just learning answers and absorbing information, that we could develop skills. We could develop characteristics. We could develop ways that our student can think about things. We can develop the skill of observation and data collection. That's hard to do. You have to do it well. Judging and analyzing information. How do you know what the information is saying? Nobody ever practices that, right? But that's what the scientists all have to do. But we don't learn that in school, right? Cooperative inquiry. We can teach them how to work together. It's not a competition who can get the best grade. It can be, we can work together to try and figure out an answer to a question that has been posed. Confidence and humility. You can learn the fact that I have gotten an answer that I think is true, but sometimes I make mistakes. That is something that you can learn if you are in the process of trying to answer some question that has been posed to you. You can learn philosophical and historical context. By learning those contexts, it brings alive the subject matter. It's like, oh, these guys were debating too. They didn't know. They were trying to figure it out. These were real human beings pursuing a real human endeavor. Then science looks like a human activity which may be engaging and interesting as opposed to a set of dry facts. You can compare theories. I mean, if they're in school, maybe they don't know, maybe they've read it, I don't know, maybe they don't know whether or not when you open a bellows, I don't know if you guys are familiar with it, you plug the end of the bellows and you open it up, you can't open it, right? Because is it because nature abhors a vacuum and you just can't create a vacuum? Or is it because there's a whole bunch of air above us that's pushing down and forcing the bellows closed, and it's really hard to push against the pressure of the air? Those are not really obvious answers. That could be a really interesting question. Compare those theories. Which one is correct? And how do you know? And what are the reasons why you believe that sort of thing, right? You can ask questions and encourage curiosity. You can help them develop an appreciation of nature and order. If any of these things were possible in a school curriculum, and I have no idea whether they are or not, because I'm not there. You guys are there. You guys are the ones that are doing it. But it seems to me like this could be a goal, a valuable goal. Any of these things would help them develop skills, develop a way of thinking about things, give them the opportunity to be curious, an opportunity to think about science in a different way as a really human activity. So, my big encouragement would be inquiry. There are ways, if there are ways of thinking about giving them the opportunity to inquire, giving them the opportunity to figure it out for themselves, giving them, there's, well, here, I'll get on to the next slide. Well, this was something that's a little further on, but I remember doing labs. I don't know, you guys do labs in your thing? I don't know how your labs go, so I don't want to impose or think about how you're doing it, but I remember my labs. And my labs were, here's the equipment, here's the procedure, and here is the answer you're supposed to get, right? When do you have a lab that says, here's some equipment, here's a question, go figure it out? Right? You never have that lab, right? That's scary. That's a scary lab, right? Because you never know what's going to happen. Maybe it takes a long time to figure that. Maybe it's a really hard question. Maybe you have to do a bunch of things. Or maybe they're like, oh, I don't know, I'm not a scientist, I'm just a school kid, right? I don't know. Can you create a culture that allows for that inquiry, that gives them the freedom to be wrong and to work together and those sorts of things like that? So to guide somebody, to have cooperative exploration, to encourage questions and projects. I found one time, as I was looking around on my phone, I found an app. It's called Physics Toolbox. Has anybody ever heard of this app? No? It's a great little app. Basically, it uses your phone. Your phone has a little accelerometer in it, right? You guys know that? Because if you turn it different directions, it knows what's up and what's down and whether you're moving it back and forth. This app ties into this accelerometer and it plots out the acceleration in different directions. So you get the x, if you hold it this way, you've got 9.8 meters per second squared acceleration. In this way, you do it this way, and all of a sudden it's the y direction as opposed to the x direction. So you could put this in your pocket and send it on the merry-go-round and have them look at acceleration on a merry-go-round. Have them drive in a car in a circle, or jump up and down, or all these sorts of things. Drop it on the floor and see what happens. Get I don't know. I'm just making this stuff up. I don't know whether it would work or not, but it sounds fun to me. I would love to do those sorts of things, right? Lean out of pat answers and expert explanations and rigid adherence to textbooks. I am not saying, don't get me wrong, I'm not saying throw away your textbook. That's madness, right? I mean, what are you going to do, right? Oh, I have no textbook. Suddenly you have a class you're supposed to teach and you have no idea what you're teaching, right? That doesn't make any sense. What I'm suggesting is, are there ways to incorporate some of these other things? So what about, right? Maybe you guys are thinking this. I certainly thought of this. How are we going to cover all of the material, right? Because usually if you're teaching some science class, there's a set of material that you have to cover. But aren't there right and wrong answers? Do you really want to teach the students how to go about a lab and not give them the right answer, right? That sounds scary as well. Or who has the time and ability to create such a curriculum is what I'm suggesting. I'm just telling you ahead of time, I don't have that time. I'm not going to build a curriculum for you. I'm too busy doing other things. And you probably don't have that time either. You're probably busy teaching. But maybe there's a way of working together, of sitting down during, having after-school meetings or something like that, and thinking about some of these things, and maybe slowly but surely introducing some of these things into your curriculum. Maybe you already do, in which case, good on you. So here's some ideas. Historical case studies. There's a lot of historical case studies. The problem with this is that reading the historical case studies is difficult because the people who were writing with a particular language, a particular vocabulary, a particular context, and you guys and students don't know what's going on there. So I don't know if there are any good historical studies, but I think high school students are capable of reading stuff. We have a section that we read briefly about nature abhors a vacuum, and we read Pascal, and he gives this whole long description of the arguments for why nature abhors a vacuum and why that's not true. It's a little tricky, it's tough, it's not easy sledding, but at least it's accessible to some extent. I haven't really studied this one, fluid or vibration, but I think that could be an interesting one to pursue as well. Natural motion, inertial or teleological. This one is very accessible, it seems to me. What do I mean by natural, inertial or teleological? I mean, at a very young age, it seems to me like it would be appropriate to pose the question of whether or not Aristotle was right? He wasn't. But the way we look at the world is more Aristotelian, right? Because what Aristotle says is that the natural motion is down, right? And if you go sideways, what is it going to do? Stop, right? If you slide it on the table, it goes for a little while and stops because you gave it an impetus and it ran out, right? What the physics people say is that if it's at rest, it stays at rest, but if it's in motion, it will go in the same direction and continue in motion at that same direction. Well, it doesn't really do that, does it? I mean, that's not our experience, right? I mean, unless you have like nice, air track experiments and all that kind of stuff. If you work really hard, you can show them that inertia works, but most of the time it doesn't. So why not raise the question, well, why do we believe in inertia? Under what circumstances? Let's take two sides of the class. You guys be the inertials and you guys be the Aristotelians, and let's have a debate. I don't know. I'm making this stuff up as I go here. Experiences, physics toolbox, I told you about that little app. Merry-go-rounds. I mean, it is so cool to take a basketball and have a bunch of people sit on a merry-go-round and roll it across the merry-go-round, and the ball doesn't go straight. Why? Why doesn't the ball go straight? I thought inertia says if you roll a ball, it's going to go in a straight line, but it doesn't, like curves off, right? You can ask questions like that, and if they're doing it themselves, they can see it, they can feel it, they can experience it, they can ask questions like that. There was a great little experiment that I found in a book one time about Scotch tape. You can talk about the two charges. There's positive and negative charge. Well, we all know that. How many of you have run into a positive and negative charge? I mean, all you know is you plug the thing into you have a battery and one says plus and one says minus or something like that. That's just what's given to us. But there's ways of doing Scotch tape where you put them together and you rip them apart and then you hold them close and they like attract to each other. Or if you if you have three of them and you rip them apart, then some of them are attractive and some of them are pushing away. And you can start exploring, why do they do these things? Why are there charges? How do these charges separate? What's going on there? These sorts of things are really hands-on kinds of ways of exploring these questions. Again, these are just ideas. It's hard work. Conclusion. I think that this style could be more engaging. Students don't have to compete and compare. I will be honest here. I remember when I was in school, it was competitive. It was not explicitly competitive, but everybody was looking around to see who got the best grades and who was the smartest in the class, right? And I will say I had a certain amount of pride because I usually did pretty well, right? And that boosted me up because I felt, oh yeah, I'm pretty good. I'm towards the top of the class. In a cooperative adventure, everybody can work together. right? It doesn't have to be a competition. It doesn't have to be who can get it doesn't have to be even a personal competition to see if I can get the highest grade that I can get. It can be, let's try and figure it out together, that kind of thing. You can decide that it's okay to make mistakes, and that you can be creative in physics, that there is a lot of creativity in science, problem solving, thinking outside the box, being an independent-minded is such a huge value, to have students who are independent-minded as opposed to slaves to the knowledge that they have been given, right? Am I the kind of person who just knows what I am told, or am I the kind of person that can think for myself? I realize that I have put the bar way up here, I know that, and I'm not having any expectations. I don't know whether this is useful at all to you, but it seems to me like the goals, in my opinion, the goals of developing our students are so valuable that it's worth at least thinking about how one might go about doing some of these things, of brainstorming together to come up with techniques or methods whereby you could pursue something like this. So now, I would really love to hear from you guys if you have questions, or if you have ideas or thoughts or feedback or pushback, or, you know, Chris, you're just nutty. I don't know what you're talking about. That doesn't make any sense. We can't do that kind of thing. Yeah, I would, because you guys are in the trenches. You're the ones that are doing it, and I'm not. I'm just up here spouting some very highfalutin ideas. But anyway, I would really appreciate any thoughts or interactions that you guys might have on reflections on what it is that I have said here. So that's what I got to say.